Hello everyone, welcome to this video. And in today's video, we will be continuing our discussion from our previous video, that is finding the majority element in a given array. But in this video, we'll be using the binary search tree method. So let's see the concept first. So I'm using the same example from our previous video. So this is my array, and in this array, I have five elements. And the majority element to be for an element to be qualified as the majority element is the frequency of its occurrence must be greater than n by 2, where n is the length of the array. In our case, we have five elements, so it should be at least three. It should occur at least three times. So we can see clearly that the element occurring three times is 3. So this is occurring three times. But how do we do it with the binary search tree method? So for that, we need to traverse this entire array and we need to create a binary search tree out of this array elements, and then we need to traverse that binary search tree to find out the majority element. So let's see that. So let's start traversing the array. So here is my first element which I encounter. So I take this element and then I create a node. Okay, so here is our customized node which is having two elements in it. One is the data element which is 3, and the other is going to be the count element, which is nothing but the frequency of occurrence of that element in the binary search tree. So here I am initializing my count with the value 1, and then I'm traversing further. So further I'm traversing, and then I find my element to be 3 again. So I will compare. So this is the normal binary search tree comparison with the root and the left subtree and then the right subtree. So I will compare with the root 3. Okay, I found it to be repeated, so I increment the count. Instead of ignoring it, I will just increment the count. Now then I will traverse further, and then I see the element 4. Then I'll compare it with the root. Okay, 4 is greater than 3, so I should insert it in the right subtree, and then I'll create another node for 4. Created another node for 4 with 4 as a data element and its count as 1. Then I'll further traverse this tree and I'll find the next element to be 5. Then I'll compare it with the root element, which is 3. 5 is greater than 3, so I should traverse the right subtree. Then I'll go further, and then I will see 4. So 4 is also less than 5, that is 5 is greater than 4. So I will make 5 as part of my right subtree because there is nothing further to traverse in the right subtree. My 5 data element inserted into another node in the right subtree, and then I will further traverse this array. So I find the element, the next element to be 3. So I compare it with the root. Okay, so this is a duplicate element again, so I will increment the count instead of further traversing. So here I have inserted the final element into this subtree and updated its count. So I have not inserted the duplicate element, only updated its count. But yeah, so we have processed the final element as well. This is how our binary search tree will be looking. So you can see here each element has its frequency of occurrence in the binary search tree as well. So we can clearly see 3 occurs 3 times, 4 occurs 1 time, 5 occurs 1 time. So clearly by looking at the count of that particular data element, if we traverse this search tree and at every point if we see the count and we compare it with this value n by 2, and if we find any count value which is greater than n by 2, then we can simply return it because we know the fact that majority element can be only one in a given array. So let's traverse this binary search tree. So first I'll start with the root. So I find this element 3, and its count is also 3, so which is what we are expecting, right? So I simply return this as the majority element. So that is how this binary search tree technique works. Here we are done with our program. So the time complexity, if you see, we are actually traversing over this entire array A. So it's going to take so if n is the length of the array, then it's going to take big O of n time complexity, and for inserting each node it's going to take another of in worst case it's going to take big O of n, where we end up inserting each node, that is we will be having a skewed tree. If we have a binary search tree which is balanced, then will be this operation of insertion will be taking log n time. So in case of balance, so all it will be taking big of n into big of n, that is big of n squared time. In case of non-balanced binary search tree, in case of balanced binary search tree, it's going to take big of n into big of log n, that is big of n log n time. And of course we have to store all the elements in the array. In the worst case, we might be ending up storing all the elements might be different, so we might be ending up in the worst case storing all the elements. So the auxiliary space complexity is also big of n. And in our case we have only stored the three elements instead, even though we had five elements, because we had duplicates. So in the worst case it might be equal to the entire length of the array, because we will then be having all unique elements in the array. So that is the auxiliary space complexity, which is occurring because of creation of a new binary search tree altogether for all nodes in the given array. So now let's look at the code part of this. So in the code, I have this find majority element. So I have a binary search tree class that I have written this find majority element. So here, if you see this, I am taking the first variable expected count, which is nothing but this one, n by 2. So I'll be using this further down in my code. So this is the expected count, and then I'm traversing the entire array, which is this traversal. Then each element I'm inserting into the binary search tree. Okay, so this is what I've shown you previously. And then I'm doing the traversal of a tree. Here I'm doing the in-order traversal, and that will return me the majority element by checking the count of this particular data element, each data element in the traversal, during the traversal. Okay, so if the majority element exists, I'm printing that, or else I'm saying it doesn't exist. Now let me show you the insert and the in-order traversal method. So here I have my binary search tree class. In that I have defined the class node. So everything is similar to the normal node structure, except I have the count variable extra in this, and in the constructor whenever I'm inserting the new node, assigning its count to be 1. And in this class I have the insert method as well. This is a recursive insert method. This is the normal recursive method which we use for the binary search tree, except this part wherein I am actually incrementing the count of that particular data node if I find it to be a duplicate. Rest else is the normal binary search tree insertion. And in the traversal method, everything is the same as the binary search tree in order traversal, except this part wherein if I find the count to be greater than the expected count, I'm just returning that data element because that is the majority element. Okay, so this expected count I have defined in the find majority element over here, which is nothing but n by 2 from this example. So yeah, so here in this in order traversal, in case if I don't find any majority element, then I'm returning the default as some unused value. You can use here. I'm using integer.min value. You can use any value you wish to use. So to indicate that the majority element doesn't exist. So then just if you find the unused value as the majority element, then print uh, the majority element doesn't exist. If you don't find the majority element to be the unused value, then yes, then you have found the majority element, so you just print that majority element. So let's see the main program for this as well. So here is our main method. I have the array from our example. I have the binary search tree class, then I invoke the find majority element on that particular array, and let's see the output. So here is the output. Majority element is 3. Yeah, so that's about the finding the majority element using the binary search tree method, which is going to take a big of n squared time complexity, wherein is the length of the array, space complexity is n. For self-balancing binary search tree, we have time complexity as a big of n log n, wherein is the length of the array, and space complexity still remains the same, that is big of n. Yeah, so that's all for this video. Thanks for watching.